Let's go live now, get a sound check going. Sound check. Sound check, sound check. Sound check. Just going to play the old wait for X to catch up game and then we'll get started. Howdy check. Hope you're doing well. I'm going to get started in about 6 minutes when X will catch up and actually start streaming the output. How's it going? All's well? Hope everyone's having a good time. as well. Good, good, good. Good to hear. Good to hear. Want to hear it. Hope everyone's having a good day as well. We'll be getting back on the data structures and algorithms course. We got through 10 chapters of it so far. Oh wait, hold on, no, it's all a lie. Oh, we didn't finish linked lists. That's where we'll get back up to. Did we not finish linked lists? That's interesting. I thought we had finished it. Don't know how we missed something. All right. Well, we'll start from linked lists and then we'll finish linked lists and then we'll get back onto a binary tree. You're looking to learn DSA as well? Yeah, cool. We'll join in. Hopefully, you'll learn something along the way. We're just on the chapter about linked lists, so we'll get back. Like I said, we'll get onto that in when X, Twitter, whatever you want to call it, plays catch up, and then we'll get into it. How's it going so far in your journey? So if I follow your live streams, that'll be enough for me to learn DSA. Nope. I would say absolutely not. Like, it's nice when you guys like join the streams and we have like a chat. We can kind of go through things and stuff. But for your own learning, I want this to kind of like serve as me. This is kind of just like proof of my work, and things, and like I can share lessons, talk through things, have discussions, all that and stuff. But if you're learning something, you got to learn. You got to learn off your own back in terms of you got to put hands to keyboard, solve problems. You can't just watch about things. You got to be doing things yourself. You got to do more than that. So I'd highly recommend Boot.dev course. It's been amazing so far. I've never really done a formal sort of like data structures and algorithms like kind of course before. It's never been necessary for me for what I've done. But you absolutely have to put pen to paper. So if you sign up for Boot.dev and you want to learn it, jump straight to that course. It'll give you a great founding. It's done really, really well for me. Really enjoyed it so far. You have to you have to put some sweat in, put some effort in. Yeah. Oh yeah, sorry, no, this isn't the today is not the start of me doing the data science at you data structures and algorithms course. I've already done a couple of episodes. If you want to go back through, if you go back through the channel, you can see the previous live episodes that I did with the other parts. If you want to catch up on those, but this is not the start. Like we're already kind of part way through this sort of course. So Right, let's see if I poke to where it will start. Yep, started. Cool. All right then. Yep. Yep. I see what you're saying, Shaq. Yeah, I know there's already a lot of streams. I'm not saying go back through all of them, but there's ones that start with the data, data structure and algorithms. I think I'm only doing 2 or 3 sessions maybe of this, but in terms of any YouTube channel, of course, I don't know about any YouTube channel that kind of covers it in full. I'm sure you can probably find a data structures and algorithms thing on YouTube, like tutorial, mega tutorial or complete guide on YouTube somewhere and stuff. But course wise, Boot.dev, that's the one I'm like pushing in the minute stuff, and I'm doing myself. Proofs in the pudding. You're actually putting pen to paper and doing it. So that's the thing I highly recommend the most. Just watching stuff is not going to be enough for anyone, so don't get into that trap. Okay, right, we got to it now, so let's get rolling. All right, so I thought we finished off linked lists last time, but looks like not. So we're on lesson 8. We had 3 more of this, so two quiz questions and one sort of like functional part here. So we're just gonna get the rest of that done now. So remove from head. So we're one method away from having full function. I'm sure we did this last time, but anyway, we just need a way to remove the first element from the linked list in constant time. When we're finished, our linked list will fulfill the basic requirements of a queue. Add to tail, constant time insert, remove from head, constant time pop. Let's rename linked list class to LLQ. So we've already done that. I remove the add to head functionality because queues don't allow inserting into the wrong end. We've also flipped the arrows in the printed representation to reflect the change. So complete the remove from head method. It should remove the first node from the list, the head, and return it. The head should now point to the next node in the list if there is one. So what was wrong with this? Oh, maybe we... Did I... Okay. Oh, we have passed this. Right, okay. Something was weird with Boot.dev then. It was like it's like treated as if I hadn't completed those ones, but now it has, so hey ho. We carry on. Right, so we were on trees. I'm sure we were on binary trees. I was really confused about that. So I think today let's try and smash through, and we'll see, because there's quite a lot of things in this one actually. See if we can get through 3, so chapter 10, chapter 11, chapter 12. Let's see, so now we're on trees. So trees are a widely used data structure that simulate a hierarchical, tree structure. That said, they're typically drawn upside down. The root node is at the top and the leaves are at the bottom. Trees are kind of like linked lists in the sense that the root node simply holds references to its child nodes, which in turn hold references to their children. But tree nodes can have multiple children instead of just one. A generic tree structure has the following rules. Each node has a value that may have a list of children. Children can only have a single parent. Makes sense? A tree, so drawn from left to right. A linked list is just node to node to node. Tree drawn from left to right, select node, and that way and stuff, okay? Multiple nodes in a tree can have the same value. Nope. Oh no, sure, why not? Multiple nodes. I suppose there's nothing to say they can't. Okay. Multiple nodes in a tree can have the same value. Yep. Parent nodes have children, and the children have parents, so multiple to 1. 1 parent, multiple children. So binary trees. So binary trees aren't particularly useful. aren't particularly useful data structures unless they're ordered in some way. One of the most common types of ordered tree is a binary search tree, or BST. A BST has some additional constraints. Instead of an unbounded list of children, each node has at most 2 children. The left child's value must be less than its parent value. The right child's value must be greater than the parent's value. No 2 nodes in the BST can have the same value. By ordering the tree like this, we'll be able to add, remove, find, update, find and update nodes much more quickly. Okay, so let's have a listen.
Unbeknownst to our programmer humor, binary trees are actually used in the real world, not just as fodder in code style interviews. Binary trees are the quintessential data structure. They're the ultimate tool for efficiently storing and organizing data. Unlike stacks or queues, a binary tree can be searched for a specific item and can be searched quickly. Binary trees are made up of nodes where each node contains a value and references to at most 2 other nodes, which is what makes it a binary tree. Those 2 nodes are called the left and the right children. The top node is the root, and the tree grows down from the root. So what makes binary trees fast? Well, it's that they are always pre-sorted. Every node to the left of a parent node has values less than the parent, and every node to the right has a greater value. Sometimes a binary tree just stores numbers, which makes greater than and less than operations really simple, but usually they store more complex data like employee information. But when they do, we just need to pick an ID, which is just a number, to sort by instead. This less than, greater than structure is what gives binary trees their fast searching capabilities. Let's say you're looking for the number 6 in a tree. You start at the root and move down, and at each node you decide whether to go left or right by comparing 6 to that node's value. Each time you make a comparison, you're eliminating half of the tree. We don't have to compare against every node in the tree, just 1 node in each level of the tree. This process is called binary search, and it means that even in the worst case, the number of comparisons is limited to the height of the tree. In big O terms, that means that it takes order log n time to search the tree instead of order n for linear time. If there are 1 million items to search, and each comparison takes 1 second, then a linear, or order n, for search takes almost 12 days. With a binary search tree, it takes about 20 seconds. But it's not just the searching operation that's fast. Inserting, updating, and deleting are all order log n as well. That's why binary trees power databases, file systems, and even Google searches.
Let me listen to that bit again.
The tree. We don't have to compare against every node in the tree, just 1 node in each level of the tree. This process is called binary search, and it means that even in the worst case, the number of comparisons is limited to the height of the tree. In big O terms, that means that it takes order log n time to search the tree instead of order n for linear time. If there are 1 million items to search, and each comparison takes 1 second, then a linear, or order n, brute force search takes almost 12 days. With a binary search tree, it takes about 20 seconds. But it's not just the searching operation that's fast. Inserting, updating, and deleting are all order log n as well. That's why binary trees power databases, file systems, and even Google searches. While you don't get those sexy order 1 operations that you would get with a stack or a queue, at least you can search the thing. Something that stacks and queues don't allow.
Very good. So nodes in a binary tree can have at most child nodes, so it's going to be 2. Same video again, so we don't need to watch again, just answer the question. Binary search trees, as opposed to generic trees, must be unordered, randomized, ordered, left child, right child, parent, left child, parent, and right child. I guess it's that, left child, parent, right child, in terms of value. So, so insert nodes. The building blocks of BST are nodes. Our implementation, in our implementation, we only use a single class, the BST node class. Any BST, excuse me, it's been a long day. Any BST node is technically also a full binary search tree. With itself as the root node, it's not aware of any potential parents. All our methods that traverse the tree will do so recursively. Have fun. Oh, great. Our locked-in BST node. So throughout this chapter, we'll be building a binary search tree to power locked-in's custom database. Locked-in's management doesn't trust the so-called open source, so here we are. One of the primary features of databases is the ability to look up records by a single key. The binary search trees are the most common way to implement these fast lookups. Each node in our BST will represent a locked-in user. A BST node has three properties. Value, the value of the node, a user object in our case, see user.py. You'll notice that users have a name and an ID. Comparison operators are already implemented for you on the class. So you should be able to compare user objects with double equals greater than less than direction. So look at that. Oh yeah, okay, yep, taps into the main thing. With thingies directly. The ID is the value that we use to determine the order of the nodes in the tree. So left, the left child node, another BST node or none. Right, the right child of the node, another BST node or none. Assignment, so complete the insert method of the BST node class. It takes a value as user class as input and adds it to a new node if the value doesn't already exist in the tree. So if the node doesn't have a value yet, just use the given value and be done. Okay. So if so we're doing if self dot value is equals none. Then I guess just use it. So self dot value equals val, and then return. If the node's value is equal to the given value, just be done. No duplicates allowed. So if self dot val is equal to val, then return. If the given value is less than the node's value, and the node doesn't have a left child, create a left child node with the given value. Okay, so if self dot left dot value is equal if self dot val self dot left is not equal to none, and self dot left dot val is what is it? So given the left given if the given value is less than the node's value, I'm not sure this syntax is quite right, but if the growling value is less than the node's value and the node doesn't have a left child, yep. So then self.left equals value. The given value is less than the node's value and the node does have a left child, then recursively call insert on the left child given value. So then so if self.left is not equal to none, and val oh, 1 minute. We will be back. Important job of the day first. Right, important job done. Back to it. Okay, so again, I'm not totally sure if is thingy. So I think we've done that recursively, but since we already checked if the given value is equal or less than the node, the value must be greater than the node. Handle whether or not the node already has a right child. So I guess if self.right is not equal to, if it's equal to none, then I guess self.right equals val. So let's run it. Whoops. Line 18. What did I do? Oops, yeah, assignment. Whoopsie daisy. User has no object, right? Oh, it's complaining app. User object has no attribute, right? Not sure what's going wrong here. So it's essentially saying user object has no attribute, right? Executed line 19. So here essentially. Suppose we just do this. So printing val. Okay. We do self.val. Whoops. Finger on the wrong button. None. Let me have a look at classes again. I can't remember exactly how the things work. Um, So Python magic methods. So you have to use it as a method with a call it as a function. Oh, all right, okay, we don't need to have this distinction of left and right. Oh wait, no, that's right. So we passed the full thing. So what was the problem? The problem at line 19. So this user object has an attribute right. Right, so what's with this part? So if the given value is less than the if the given value is less than the node's value, and the node does have a left child, recursively call insert on that left child with the given value. Recursively call insert on that left child, the given value. I mean, that looks right. I'm not sure what the diddly is. What's wrong with it? So let's start from the top. So if the node doesn't have a value, if the node doesn't have a value yet, just use the given value and be done. So self value equals value. If the node's value is equal to the given value, just be done. No duplicates allowed. Very confident in them. If the given value is less than the node's value, and the node doesn't have a left child, and create a new left child node for that new value. Pretty sure that's spot on. If the given value is less than the node's value, and the node does have a doesn't have a left child. Oops. So if the given value is less than the node's value, the given value is less than the node's value. Hold on. If the given value is less than the node's value. If the given value is less we've already checked if the given value is equal or less than the node, the value must be greater than the node. Handle whether or not the node already has a right child. If the is equal to none, then we set what is wrong with that? The only part that references the right is here. So it's problem at self.right. User object has no attribute right. I'm not sure exactly what the problem is here. And I'm running out of steam. Alright, just so we don't get stuck all night, I'm going to call in Boots. I'm stuck again. Come on, Boots. I see your code encoder. Let's work this thing together step by step. A curious error appears. Attribute user object has no attribute right. Let me ask you. When you want to add a value to left or right child, what kind of objects should self.left and self.right be? Should it be a user or something else? Spend a moment considering what type each child should hold in a binary search tree. How might you create a new node properly for the left or right child when inserting? What do you want to try and fix first? Oh, I suppose it's just the... It doesn't have like a... Your choice. Let's focus on the root problem. When you sign self dot left or self dot right, you're assuming a user object instead of a BST node. Okay. Right, yeah. Oh, right, I see. What would happen? Right, okay. Okay, I made a really... This is probably just how tired I am. Yeah, of course it's a node. You're gonna pass the instance of the class there. Oh, okay, well, I got further than last time. So fail. Both failed. So if the given value is less than the node's value, and the node does not have a left child, recursively call insert on the left child with the given value. Call insert on the left child with the given value. I say fixed that silly on my part. Could you corrected the child sign, but something still isn't quite right. Let's focus on this part. Here we're replacing self.value, which should be a user, with the new BST node. So your tree node's value is no longer a user, but a whole BST node. That's why your output prints. All right, okay. Think about this. What shape? When should you create a new BST node, and when should you just store the self? Right, okay. Yeah, I'm definitely not functioning quite right yet. So I guess these are not the time when we want to use a BST node. No, actually, hold on. No, that's right. Uh, what type should self.value be after inserting a value? When should you create a new BST node, and when should you just store the self.value? Try additioning code to the root. There's no value, you just assign the user object to self file, and now not a new BST node. When you go left or right, only then do you create a new BST node as a child. What change would you make if self.value equals non-clause? Oh. Ah, come on. I'm almost there. You're getting closer. Your instincts about where to use are sharpening. But let's focus on two important issues. So self.value equals on the top. If you're putting BST node inside self.value, when self.value is supposed to be a user. Okay. You should do self.value because self here, not right. Okay. Get the right, get the stick. When you recurse, you have but you only ever want to insert the user value into. Okay, right. Get rid of that. So always pass the user in. Key point, self.value is already user or none. Self.value left to right. Okay. Left insert value, left that. Is that all working now? Nope, still not quite for some reason. What would happen if whenever you're calling insert, you pass user, not a node? Are we there yet? A very close traveler, there's just one nagging issue. A tree is ending up with duplicate insertions and incorrect child logic. Let's focus on this block. You're always creating a right child if one doesn't exist, no matter what value you're inserting. So values that should be on the left might be on the right, and so on. You might always make a right node even if there's values. Make a right node even if the value is less than self.value. How could you change your logic so the right child only gets created if the if the value is greater than self.val and there isn't already a child? Okay, so it didn't say they needed to check the value as well, but anyway. So value is greater than self.val. Bonus, what do you still need to do if the right child exists and the income value should go right? Ah. There we go. Right, okay, just had to extrapolate out. Not take the instructions so literally. Okay. Okay, so insert review. So inserting into a binary tree, like most of its operations, is very fast. Picture the algorithm that you just wrote in your head. How many comparisons does it take to find the right spot for a new node? So inserting into a binary search tree, like most of its operations, is very fast. Picture the algorithm that you just wrote in your head. How many comparisons does it take to find the right spot for a new node? It only requires one comparison for each level of the tree, making O log n! Exclamation mark. At least in a balanced tree. We'll talk about this later. Order log n is very fast. It's practically as good as O1 in most cases. If our tree has a million nodes, we only need 20 comparisons to find the right spot for a new node. If our tree is 2 times larger, 2 million nodes, we only need to make one more comparison per insert. 21 in total. So, what is the average big O complexity of insert method? Oh, 1, right? Whoops. Oh, log n. For comparisons and insert. Okay. Min and max. Some of the simpler BST algorithms are the get min and get max methods. So the assignment is, now that we can add users to our BST, now we can add users to our BST, our systems team wants us to start implementing search functionality. Implement the get min and get max methods. They should return the minimum and maximum values in the BST respectively. Okay. Get min and get max. So I guess with this, it's a case of get min is about recursive traversal. So if I guess if self dot left is equal to none, then return self dot value. Else, I guess. Because So now that we can add users to our BST, our systems team wants us to start implementing search functionality. Implement the get min and get max methods. They should return the minimum and maximum values in the binary search tree respectively. So I guess get min, so if you look at the left, if the left node is none, then the smallest number is the current value. But if there is no left value, then we call self.left.getMin. Yeah. Non-type object has no attribute username. They're not just as simple as that. Implement the get min and get max methods. So here you have the current node. If there is no left node, then just return the value. It should just return the value of the current one because there's no further left you can go, right? And then if it's not, then you loop back around, you take the left one and get the min from that, and you just keep going until it ends. What's wrong with this? Let's get a tip. The get min function loops through all the left child nodes and returns the value of the last one. The get min function loops through all the left child nodes and returns the value of the last one. Get function max does the same for the right children. Let's just print it. So print howdy self.left. Need a return statement on this? Well, there we go. Needed to return it. Okay, so I was on the right lines. Delete. So, oh my goodness, how many are there? Oof. Right, so delete. We also need a way to remove users from our BST if a user decides to delete their account. So the assignment. Implement the recursive delete method. it takes a value as an input and deletes the node with the value if it exists. Each call returns the new root of the tree or subtree after the deletion. Notice that in the test suite, the delete method is called like this. Okay, so delete. So check if the current node is empty, has no value. If it is, return none. This represents an empty tree or a leaf node where deletion has already occurred. So I guess if check if the current node is empty. It's equal to none and return none. If the value, the current node is empty. Okay, so if the value to delete, if the value to delete is less than the current node's value, if the value to delete is less than the current node's value. Okay, so if value is less than self.value, if there's a left child, recursively delete the value from the left subtree and update the left child reference with the result. If there's a left subchild, so then if val dot left recursively delete the value from the left subtree and update the left child reference with the result. Okay, if there is a left child, recursively delete the value from the left subtree and update the left child reference with the result. What? Return the current node. There's a left. If there's recursively delete the value from the left subtree and update the left child reference with the result. I dot delete I dot left return current node and update the left child reference with the result. If the value to delegate is greater than the current node's value, so if value is greater than self.value, if the value to delete is greater than the current node's value, there's a right child, recursively delete the value from the right subtree and update it. Okay. If the value to delete equals the current node's value, we found the node to delete. So then if the value is equal to self.value, then if there is no right child, return the left. So if dot right is equal to none, then return value dot left. If there is no left child, turn the right child accomplish anything. So if then return value dot right. If there are both left and right children, we need to find the new successor. We need to find the new successor, the smallest node in the right subtree, which is the value next largest after the current node's value. Oh my goodness. Ugh. So if both left. Okay. If they are both left and right child, we need to find the new successor. So if value dot left is not equal to none and value dot right is not right is not equal to none, we need to find the new successor, the smallest node in the right subtree, which is the value next largest after the current node's value. Jeez. So then find the smallest node in the right subtree by walking down the current right child's left right until reaching a node with no left child. Place the current node's value with the successor's value. So should we put successor equals value dot right? So we do while loop, so like while the child replace the current node's value with the successor's value. No, that's not right. How do we traverse? Oh my goodness, what the heck? Run? So find the small. So if left hand means find the new successor. The smallest node in the right subtree. The new successor, the smallest node in the right subtree, which is the value next largest after the current node's value. Okay. So I'll put that back. Successor equals so it's going to be self dot right. Find the smallest node in the right subtree while walking down. Current right child's left. Right. Not sure how to go about this. So find the smallest node in the right subtree by walking down the current right child's left branches until reaching a node with no left child. I have to use a while loop or something. So replace the current node's value with this successor's value. So I guess while value dot left in I can't get my head around this. Not at all. I got this, but blimey. So if there are both right and left, if they're both left and right children, yeah, we need to find the new successor, the smallest node in the right subtree, which is the value next largest after the current node's value. So find the smallest node in the right subtree by walking down the current right child's branch. Got any tips for this? Oh my god. Find the smallest node in the right subtree by walking down the current right child's left branches until reaching a node with no left child. Place the current node's value with this successor's value. Delete the successor node from the right subtree, or recursively calling delete, and update the right child reference with the result to the current node. Melting my brain here. It's this part that's tripping me up. So how do I walk down it? So find the smallest node in the right subtree by walking down the current right child's left branches until reaching a node with no left child. Current right child's left branches. Okay, my brain is not working. Can you help? Oh, it's not a good night. Okay, I see your code in the error message. Usually has no attribute left. Take step back and reason about the delete method on the BST should do. Right now, in the lines, if value left is not equal to none, you're using value left, but value is an instance of user, not a BST node. All the logic for traversing left-right child needs to be children needs to use self.left. Whoops. When you want to go left, alright, okay. All the logic for traversing left and right children needs to use self.left and self.right, not value.left or value.right. To get started, when you want to go left or right, which property represents the left child of a node? Try focusing on just correcting this first part. Make sure you're always traversing the tree using self.left and self.right. Can you update the delete method so that the tree verse will use the correct references? Give it a shot. If there is no right child, return. If there is no... Right now. We're making progress, but still still has some critical issues with how you're traversing and updating the tree. Let's go step by step. So incorrect usage of value left and value right. You're still writing value left in your traversal box. Right, okay. Ugh. When deleting in a subtree, must assign the result of the recursive delete callback to the correct child. Otherwise, the possible changes, like removing the node, won't be reflected in the parent return value. At the end of each branch, you must return self unless you're actually deleting the current node. Then you may return the new child in its place. So that's the key question. If you want to recursively delete value from the left subtree, what exact statement should you write using only self less than self right? Try fixing else if block at time, focusing on the BSC no properties, then see how your magic lock falls into place. Okay. Improved. You're getting closer, but you have a key misunderstanding about how recursion children work in a binary search tree. Let's use some Socratic questioning to guide your thoughts. Look at this bit. So, if self dot left is not equal to none, then self dot delete self left. What does this line actually do? Which node are you trying to delete the value from? If you want the left subtree to update, don't you want to write something like self dot left is equal self dot left dot delete value? I have no idea. So self dot left equals self dot left. Another hint. Remember, you want to call delete on the child node passing value as the argument, not the node itself. Try stepping back and write what the recursive step should look like if you want to recurse into the left child and update the left pointer. Better. You're much closer. You're now correctly updating the child pointers with however, you have a few more improvements to make. Return the value from recursion. So you currently return self.value. After the recursion, but you should always return the node self, not the value. The return type is what is expected for the BSC node and all. Okay. Successor handling for two children. So your handling for two children case is not completed. Right now it's this, yeah. So it doesn't actually do anything. It will cause infinite loop if hit. Think, what if the successor in a BST, what is the successor in BST when deleting a node with two children? What is this? How could you find the minimum value in the right subtree? Once you find it, what should you do with it? You already have a getMin function. Can you use self-write getMin here? Yeah, I was thinking about that. After replacing the value, so once you set self.value to equal successor value, remember you must actually delete the successor node from the right subtree to avoid having a duplicate value. So then self.val equals successor. So far off. You're really close. You did an excellent job with recursion and successor logic for the two children case. Your main bug, you find the successor with that, but then when deleting it, you write, whoops, copy and paste issue. Oh god, that was painful. Don't think I quite got my head around the recursion of that in terms of code wise, but with Boots' help, we move. Anyway, so god, binary trees, yuck. So the delete method is O log n because, like most binary tree options, we don't have to search the entire tree. We only have to search one path from the root to the leaf node we want to delete. The depth of the tree on average is equal to log base 2 of the number of nodes in the tree, for example. We only need to use 10 steps to delete a node from a tree of 1,000 nodes. What is the approximate depth of the tree with 16,000 nodes? What's that doubling? So by 12 it's by 13 it's 9,000-ish. About 14. Let's get it to explain. So great insight, let me break down why 14 levels is the correct answer. The key insight is understanding the relationship between the number of nodes and the depth or levels of a binary tree. Selection explains the depth is approximately log base 2 of the number of nodes. So for 16,000 nodes, we calculate log 2 16,000. Let's work through step by step. Look at the table from the lesson, we can see a pattern. 1,000 is 10, 2,000 is 11. Since 16,000 between 8,192, which would be 13 levels, and 16,384, which would be 14 levels, you can estimate that 16,000 nodes would require approximately 14 levels. To be more precise, is 13.97, which rounds to 14. Why the other answers don't work? Yeah. Which is the average big O of the delete method? It's O log n. So the delete method of O log n, because the most because like most binary tree operations, we don't have to search the entire tree. We only have to search one path from the root to the leaf node we want to delete. This the depth of the tree on average is equal to log base 2 of the number of the nodes in the tree, for example, like that. So excellent question. Let's delve into why O log n is the correct answer for the average big O of the delete method in the binary tree. So big O notation describes how runtime or space requirements of an algorithm grow as the input size grows. In the case of O log n, it means that the time it takes to complete an operation grows proportionally to the logarithm of the number of elements in the data structure. For deleting a node in a binary tree, you don't have to look at every node in the tree. Instead, you only need to traverse a single path from the root down to the node if you want to delete, or where it would be if it existed. Think of this like every time you make a decision at a node, go left or right, you effectively cut the remaining search space in half. This halving of the search space is characteristic of logarithmic time complexity. The lesson explains it beautifully. We only have to search one path from the root to the leaf node we want to delete. The depth of the tree on average is equal to log base 2 of the number of nodes in the tree. This means that even with a very large number of nodes, the number of steps required to find and delete a node remains relatively small. For example, as the table shows, to delete a node from the tree of 1,000 nodes, you only need about 10 steps. That's a very efficient process, hence log n, O log n. Would you like to explore the Boolean notation? No. So pre-order traversal. A pre-order traversal is a way to visit all the nodes in a tree. It's called pre-order. Let's try and get to the end of this thing, and I'll probably have to call it a night because I'm struggling. It's called pre-order because the current node is visited before its children. This tree would be traversed in this order: 4, 2, 1, 7, 6. Sometimes it's useful. I'll be a bit slow to iterate over all the nodes in the tree. In the case of locked in, we've been asked to build a way to create a backup of our database indexes. This traverse will allow us to save all the data in the tree to a file. So the assignment: implement the recursive pre-order method. It returns a list of values in the order they are visited, and it takes as an argument the ordering of values we have visited so far. God. Implement recursive pre-order method. It returns a list of the values in the order they are visited. It returns a list of the values in the order they are visited, and it takes as an argument the ordering of values we have visited so far. For example, the first call to pre-order on an entire tree would be an empty list is passed in the first call. Here are the algorithm steps. So visit the value of the current node by appending its value to the visited array. Visit visit the value of the current node by appending its value to the visit. Whoops. Value. Recursively traverse the left subtree. Recursively traverse the right subtree. Return the array of visited nodes. Oh my god. Oh. Ugh. Recursively traverse the left subtree. Recursively traverse the left subtree. I'm just not understanding the recursive part. It really just isn't sinking in, which is unfortunate. But it's just me. I'm trying to think it through. So recursively traverse the left subtree. Recursively traverse the right subtree. It's the recursive part. I don't really get. I'm not getting this part. It's just not. Is not going in. This is the most I've struggled in any of it. Oh. Hmm. I guess it's just a case of dot left dot pre-order, and then you send it self dot left, and then visited like that. Ah, crap. Since list of values in the order they are visited, it takes argument. And it takes an argument the ordering values we have visited so far. Type object has no attribute pre-order. I guess I have to check stuff. So like if self dot left is not equal to none, and do that. Whoops, do that. So then if self dot right is not equal to none, and do that. Okay. Right, okay, I've decided to notice now that the instructions are kind of not giving as much hand holding. It's kind of expecting you to figure out a bit more, so I need to kind of adjust for that. Let's get to the end of this and then see how red black trees are. If it's feeling like a little bit much, I might have to just leave it for tonight because I'm just struggling. Oh. Okay, so a post order traversal also visits all the nodes in a tree. It's called post order because the current node is visited after its children. The following tree would be visited in this order: 1, 2, 1, 2, 6, 7, 4. Okay, so it goes bottom up. Okay, so assignment. Our data team didn't like the way we ordered the users in our BST export. Personally, I think they just want to get the work for themselves down the road. Anyhow, we've been asked to change it. Implement the recursive post order method. Here are the algorithm's steps. So recursively traverse the left subtree. So how did I do that in the last bit? I forgot already. Check if it's like set and then okay. So recursively traverse the left subtree. So if self.left is not equal to none, then self.left. What was it again? Self.left dot post order. And then visited. Okay. Visit the value of the current visit the value of the current node by appending its value to the visited array. So okay, so then visited dot append self dot value, and then just return visited. It's just the opposite. Okay. In order traversal. So an in order traversal is the most intuitive way to visit all the nodes in a tree. It's called in order because the current node is visited between its children. It results in an ordered list of the nodes in the tree. The following tree would be 1, 2, 3. So in a send in order, value order. So in order, recursively traverse the left subtree. So if self.left is not equal to none, then self.left dot in order visited. And then visited dot append, and then it's self dot value, and then it's about doing the right side, and then return the full list. Return visited. So it's just about the ordering of how you do the recursion. Okay. The node exists. On locked in, it's common for one user to navigate directly to another user's profile. We even creepily give the stalked user a notification that someone is looking at their profile. To make this feature work, we need to be able to quickly check if a user exists in our tree. So complete the exists method. It should take a value as input and return true if the value exists in the tree and false if it does not. It's a recursive method, as you probably guessed. So don't trust below this line. Okay. To return false. So I guess if self dot left is not equal to none, then and I guess it and self dot value, whoops, self dot left dot value is equal to value so I guess the first check is if if a self dot value is equal to value, then return return true. If the self dot left is not equal to none and self dot left of value is not equal to thing, then we do self dot left left dot exists and pass the value. Then we do the same with the right. Right. In all the cases, return false. Alright, what am I missing? Okay, so it should return true if the value exists in the tree and false if it doesn't. It's a recursive method, as you probably guessed. So I guess if self.value is equal to the value, then there's a match, return true. If not, we just carry on. If we do, if the self left if there is something in self left and self left is not like that, then traverse that part, traverse that part. I'm not sure what's wrong with it. So that's boot. Close. You're definitely on the right track. I can see you understand the basic structure of searching binary tree, but there are a couple of key issues with your current approach. Look at your code. I noticed two main problems. You're not returning the results of your recursive calls. Oh yeah, dummy me. Yeah, I need to remember that. So recursive calls always need to return. Does that solve the issues? No, not quite. You're not using the BST property effectively. In a binary search tree, you don't need to check both left and right subtrees. You can use the comparison val between value and self to decide which direction to go. Here's a question to guide your thinking. A binary search tree, if the value you're looking for is less than the current node's value, which subtree should you search? Okay, fair enough. And is less than that way around? So if so if if the value you're looking for is less than the current node's value, which subtree should you set? If the value of your self.value. How about now? You're getting closer. I can see you've fixed the issue with the training the recursive calls, which is great progress. However, there's still a logical issue with conditions. Let me ask you a guiding question. In a binary search tree, if you're looking for a value that is less than the current node's value, which subtree should you search, left or right? If you're looking for a value that is less than the current. So if the value is less than there we go. Gosh. Struggling to wrap my head around this, I'll tell you that. So hi, our DevOps team has been concerned with the hardware required to run the software using our BST. In an effort to diagnose the issue, they've asked us to write a method that returns the height of the tree. For example, this tree is 2, has a height of 2 because the longest path from the root node to the leaf node is 2 nodes long. So assignment, complete the height method. It returns the height of the tree rooted at the current node. So if the node's value is none, then return 0. So if dot value is equal to 0, turn none. Whoops, 0. Recursively calculate the height of the left subtree. So if self.left is not equal to none, and return and self.left dot height. Use the max function to return the maximum of the left and right subtree heights plus 1. What? Use the max function. Use the max function to return the maximum of the left and right subtrees height plus 1. Python max max left tree. Zero. Max right tree. Return max of max left tree, max right tree. Cursively calculate the height of the left subtree. Use the max function to return the maximum of the left and right subtree heights plus 1. So recursively calculate the height of the left subtree. I'm not sure this is right. I'm gonna have to thingy to boots again. I'm gonna lose my XP, but who cares for this because I'm struggling. I see your code, and I see your code and your output. You're very close. Let's focus on what's going on using some questions to guide you. So in your height method, what happens if both self.left and self.right exist? Does your current logic consider both subtrees, or does it return early? The lesson wants you to recursively calculate both the left and right subtrees, then take the maximum and add 1. Are you doing both calculations and combining them, or are you only returning one side if it exists? Think about rearranging your code so always compute both left and right subtree heights, even if one is missing. Use 0 as the height. Only after you've got both, return max less. Can you try adjusting your method so it always calculates both subtree heights before returning? But, like, have I got anything to get the max height? I don't really understand how to calculate both and do it recursively. I spelled that completely wrong. Recursively. This is one I just don't quite get. Okay, so that's an excellent question to ponder, young coder. Recursion can feel like a tricky bit of magic at first, but it's quite logical. Let's break it down with a guiding question and a small example. Not your actual solution, mind you, but something similar. Suppose you have a tree node and you want to find the height of the tree. For any node, you need to ask, what is the height of my left child's tree? What is the height of my right child's tree? You then take whichever one of those is greater and add 1 for the current node. In this code we're calling the same functions self.left and self.right if they exist, using the return values to determine your answer. Oh, so I had the right idea, literally just that. I'm losing it. Right, okay. It's 20 to 10. We got red, black trees. Now, how much am I going to cry going through this one? There's 9 steps, so it's like, let's give it a bash and let's see how far we get before the end of the night, because I'm starting to trip up now. I hope you guys are having a good experience back out there. Hopefully it's been a little bit funny to watch my brain melt away. Hopefully learning something as well. Drop a comment in the chat if you enjoyed it so far. Just let me know. So, unbalanced trees, BSTs have a problem. While it's true that on average a BST has O log n lookups, deletions, and insertions, that fundamental benefit can break down quickly. If mostly sorted data, or even worse, completely sorted data is inserted into a binary tree, the tree will be much deeper than it is wide. As you know by now, big O complexity of the tree's operations depend entirely on the depth of the tree. So a balanced tree and unbalanced tree. Notice that both trees are valid BSTs and both have the same number of nodes. The trouble is, in the unbalanced tree, there are more levels to traverse, bringing the big O complexity closer to O n than O log of n. If 100 sorted items are inserted into a BST in order, what will the big O complexity of lookups? Sort types. Yeah, because there's going to be one for every level, right? Assuming the trees remain balanced, will a balanced tree's operations ever degrade past O again? Nope. Right, so red-black tree. So a red-black tree is a kind of binary tree that solves the balancing problem. It contains a bit of extra logic to ensure that as nodes are inserted and deleted, the tree remains relatively balanced. How it works? This is, oh my goodness. This might be another tomorrow night's problem. We'll watch the video and I think we'll leave it there because I'm gonna like just turn to mush. Create a new node. Oh, yeah. Let's watch the video and then we'll come back to this tomorrow.
So regular old binary trees have a problem. They have no built-in protection against unbalance. If you insert an ordered list into a binary tree, you'll end up with a single branch in your tree, which is no better than a linked list. Your efficient order log n lookups degrade right down to order n. But a balanced tree is a fast tree. And by balanced, I just mean it's about as wide as it can be. It doesn't have these super long branches that take forever to iterate down. So how do we keep our binary trees balanced? Well, the red-black algorithm, or the red-black tree data structure specifically, solves this. Here's the big idea. When items are inserted and removed from a red-black tree, we have one little extra step. Take insertion, for example. After inserting a new item into a red-black tree, we have a fix step. And in the fix step, we check the state of the tree, and if it's starting to become unbalanced, we perform a rotation, which is basically just where we take the longer branch of the tree and fold it back into the rest, which flattens the tree as a whole. Now, first of all, don't let the colors red and black confuse you. They're really just a Boolean value that we attach to each node, true or false. The only reason we use the words red and black is so that it's easier to draw out and visualize. The idea is that every node in a red-black tree has this extra bit of data, its color, and we use those colors to know if the tree is sufficiently balanced or not. There are just a few simple rules. First, each node is either red or black. Second, the root is black. Third, all nil leaf nodes are black. Fourth, if a node is red, then both its children must be black. And fifth, all paths from a node to any of its descendant nil nodes, the bottom of the tree, must go through the same number of black nodes. Now, that last rule, that all paths from a node must go through the same number of black nodes to reach the bottom of the tree, that's the ticket. When a branch starts to get too long, we rebalance the tree by performing a rotation to make sure it still follows the rules. So let's focus on the rotation. That's really the most interesting part of a red-black tree. Now, rotations can work both right and left, but let's look at a left rotation. A right rotation is just the mirror of it anyways. So first, we start with this tree. 4 is the pivot, and 2 is the pivot's parent, and these are really the nodes that we're rotating around. First, we update the pivot's left child reference to now point to what was its parent, 2. Next, that left child that we just orphaned, 3, we make it the right child of the old parent. And that's it, we're done. Let me show that to you one more time. Now, it's important to understand this actually happens inside of a tree. So here's a visualization of the exact same thing happening inside a larger tree. And here it is again one more time.
Okay. Well, I think with that mind melter, that'll be it for tonight. Whew, it's been a mind melter. And I used up all my baked salmon for boots because I got skill issues. But we gotta go start somewhere. This is definitely my weak suit, but I'm not afraid to admit it. I'm not afraid to show it. I'm not afraid to be on here with you guys and get better at it and stuff. So we're back tomorrow night. We'll be tackling that and hopefully getting towards the end of the data structures and algorithms course. And then we'll see what's next. I can't even remember what the next one will be, but we'll find out. Anyway, thanks for coming down. Thanks for watching. Like, follow, subscribe, wherever you want. Get some feedback and stuff. We're getting through this. We'll be getting through Boot.dev by the end of the year. That's the goal. Thanks for coming, and I'll see you next time. Goodbye.